Well, welcome everyone for the final part of our Tides of Innovation series. This week, we're actually fortunate to have Allison Goodwell. She is not only our capstone speaker, but she is also here in presence for us. The way this will work is I'll do the introduction, you'll have a presentation, then I'll help manage the questions online and in person. But Allison Goodwell is a visiting research scientist at the Prairie Research Institute at the University of Illinois Urbana-Champaign. Her research focuses on understanding causal interactions and dependencies in complex ecological systems based on models and data. She received her PhD from the University of Illinois in 2017 in civil environmental engineering. She was an assistant professor in civil environmental engineering at the University of Colorado, Denver. And recently she's joined us and she's received funding for both work on a CZ cluster from NSF as well as a NASA new investigator program. Allison?
Right, great. Thanks so much for having me. Everyone on Zoom can hear? I believe so. Okay, great. All right, great. Thanks everybody for being here and being online today. My name is Allison. I'm a visiting research scientist right here at PRI. And normally I work remotely, so I'm super excited to be here today and meet a few people in person. So the title of my talk today is Causal Fingerprints, Characterizing Environmental Interactions from Data and Models. Okay, so to sort of premise this, very broadly speaking, the Earth system is highly interconnected and consists of many interactions and feedbacks between different subsystem components. And we can kind of see this reflected in our own scientific disciplines. So for example, if we just pop up the about statement from the PRI website, and we look at this probably not even all-inclusive list of our scientific disciplines, this just sort of illustrates that we are increasingly recognizing that our disciplines, our data, our models, and the subsystems that we study are highly interconnected through these different types of processes, and that it's important to sort of leverage this connection to better solve interdisciplinary types of problems. So today, most of my examples are going to be sort of in the hydrology, water, weather, climate sort of subsystems and looking at causality. But generally, this talk is about data. Everyone loves data. We have a lot of data and models and understanding predictability in these types of systems and kind of agnostic to multiple types of systems. So to get started, what is a causal fingerprint? From the title of my talk, I'm going to say that just like a human fingerprint is kind of a unique forensic identifier, a causal fingerprint is an identifier of dynamics in a system. So a fingerprint is going to be a characterization of how a perturbation propagates through a system. And what do I mean by a propagating perturbation? Unless you've been living in a cave for the last few weeks, we're all aware that we've recently had a solar eclipse pretty near this area. And that's just an example of an ecosystem perturbation. This paper that I'm referencing here is actually from the 2017 solar eclipse that was in August of 2017 that kind of crisscrosses the most recent path of totality. But basically this is showing a few time series data plots from a single site during the day of the eclipse. And I'll just talk a little bit about what's going on here. The top plot is showing total solar incoming shortwave radiation. It pretty linearly drops to 0 during the time of totality. So, no incoming shortwave radiation. And on the second plot, we see some meteorological variables. And basically here we see a dip in air temperature and vapor pressure deficit along with the dip in solar radiation. Finally, we also see a dip in latent and sensible heat fluxes from eddy covariance data due to the decrease in solar radiation. And finally, we see that the atmosphere becomes very stable and it's kind of like a rapid onset of sort of nighttime conditions almost. So this is kind of a special type of perturbation where essentially we can thank the moon for having intervened on a single system component, which is literally being able to block out the sun. And we can pretty directly infer causality within the system because we can pretty clearly say, the dip in latent heat flux did not cause the solar radiation to dip. No, we know that there was a solar eclipse. So we kind of know the directionality of the chain of interactions. And we can also see that these meteorological and flux variables are sort of reacting to the solar radiation at a time lag that's usually on the order of minutes. So this is a really special example of a perturbation. But here on Earth, as humans, we generally rely on ascertaining these types of cause and effect relationships directly from our data. So luckily, we have more and more data. We are observing the system through, small statewide networks to national gauging networks of different types of environmental variables, all the way up to the NASA Earth fleet, which is measuring, global variables at a scale on the order of meters and a time scale often on the order of minutes. So we have more data than we've ever had before, and we're collecting data more quickly than we ever had before. And along with this increase in data availability, we're also increasingly interested in and able to make predictions within this system. And there's different ways that we can kind of think about making these types of predictions. On the right-hand side, I'm showing an example, or sorry, on the right-hand side, I'm showing an example of a process-based model. So this is the community land model illustration. And it's based on our physical understanding of the system or our hypothesis or our experiments of how things are working. And basically we can think of each of these arrows between these different processes as kind of being represented within the model through equations and parameterizations. On the flip side, we also have an increasing prevalence of machine learning and deep learning data, deep learning types of models. And these types of models are taking that observational data directly and hypothetically learning those relationships directly from our data set. And just as an example of kind of the increasing prevalence of machine learning approaches, this is a really new AGU, Journal of Geophysical Research journal, and it's directly related to geoscience approaches to machine learning and computation. So that's just kind of illustrating the really kind of rapid prevalence of these data-driven types of modeling approaches. Okay, so we have more and more data, we have more and more models, more and more computational power to run those models. And this allows us to address more questions related to causality. So a couple of basic questions that you might be answering now include, are the variables in my system related? Do I see a stream flow peak when it rains in a certain area? Or is my model getting the right answer? And there's different ways that you can address that question. However, there's lots of different questions that we could possibly ask. We could ask questions like, can I say that a variable causes another variable? Can I ask questions about how did my system evolve to get to where it is today? Or how did I get to my current state? I could ask, is my model getting the right answer for the right reason? And then finally, do I know the right reason based on my observations? And I would say that all of these later questions are related to causality and cause and effect relationships. So we really need to understand what's that all about and how do we start to kind of quantify the answers to these types of questions. And as a spoiler alert, from my perspective at least, this is going to be all about information, and we'll talk about what information is in a little bit. But whether that information is missing, or it's available, or it's good, or it's bad, or it's provided alone or together, or whether it's used or not used within a model. So that leads me to a little bit of an outline for today. First, I'm going to talk about characterizing causal interactions directly from our data. And then I'm going to talk about kind of translating this to a more modeling perspective and how do we look at these process interactions from the standpoint of how our models are reflecting them or not reflecting them. And finally, I'll conclude with a little bit of a kind of broader view on some causality related research directions. All right, so there are different perspectives on causality, and I'm not going to get super philosophical here with this. But the first thing, just to kind of wipe out of the way, we all have heard this a lot of times before, and it's sort of an overused trope, but it's that correlation is not causality. And the example that I'm going to kind of run with here is that if you're an alien and you are coming to Earth and you've never been to Earth before, and you see a windmill and a fan, you might kind of think that they're the same thing. And you might see, you might measure wind and the motion of the instrument, and not really be able to distinguish like which one is which, you know, like is the wind moving the windmill, or is it the motion of the wind that's causing, or is it the motion of the instrument that's causing the wind? And obviously we know that in these systems, it's kind of, they're backwards, right? So if you are Judea Pearl, and you invented the idea of Pearl causality, and you've written a lot of papers and books on this meaning of causality, you would say that you have to intervene within this system to really know cause and effect. So you would have to build a barricade in front of your windmill or unplug something, or, you know, kind of like change one variable in your system to specifically see what happens to the other variables and use that to define cause and effect. However, like we talked about with the solar eclipse, that's really hard to do. And we're going to kind of assume that generally, you know, in a natural system, our data is our data, and we are not always able to do this sort of intervention. So we're going to look at a much more statistically based notion of causality, and that's Granger causality. And in Granger causality, we can say that X causes Y. So we have two time series variables now. So we're taking, you know, wind and windmill speed data. And we can say that X causes Y if the history of X provides information to Y that's not already contained in Y's own history. So this is a statistical concept. We can actually apply this to our time series data, and we're really going to love this because we're going to kind of run with this to infer causality from our data. And the way that we're going to do that technically is going to be through a field called information theory. And information theory is based on a measure called Shannon entropy, and that's this H. And this yellow circle is not the sun, it's going to be the size of my entropy or the magnitude of entropy. And entropy is the measure of uncertainty in a random variable. Our random variable is X, and you can think of it as a time series variable. And as you can see from this equation, entropy is just based on a probability distribution function of X. So if you've ever had data and created a frequency histogram with that data, you have effectively made the probability distribution function that you need to plug in to the entropy equation and compute entropy. So the higher the entropy, the higher the uncertainty, and the more uniform your PDF, so the more your PDF looks like this kind of die roll or coin flip type of situation, the higher your uncertainty. So you might be thinking like, okay, well, that's uncertainty. What does that have to do with information? And I kind of like to think of entropy flipped on its head a little bit in terms of potential information that could be obtained, in that just maybe you have something that could reduce some of that uncertainty. So if your process is like a coin flip or a die roll, no, like unless you're cheating, there's no way of you know, reducing your uncertainty of what you're going to roll next. However, if your variable is something like rainfall, you can think about things knowing about meteorology. You can think like, well, is it cloudy today? Did it rain yesterday? And you can have a lot of sources that can reduce that uncertainty. So the way that we quantify this reduction in uncertainty is through mutual information. Now we're talking about a two-dimensional probability distribution function. No big deal, but the mutual information is the reduction of uncertainty of one variable given the knowledge of something else. So this kind of allows us to draw a link between two time series variables. Maybe one can be lagged in time, so it could be, you know, does the history of one variable provide information about a current target variable? But we're not quite at the level of causality yet. And to do that, we need to consider one more thing, and that's a measure called transfer entropy, which is a conditional version of mutual information. So in transfer entropy, we are looking at a lagged source X and a current target Y, and conditioning the mutual information between X and Y on knowing the history of Y itself. And so this lines up exactly with the definition of Granger causality. It's telling us if the history of X provides information to Y, conditioned on already knowing Y's own trajectory. So if Y's own historical trajectory could have predicted its own current value, then our transfer entropy is very small. And we can kind of conclude that, you know, these variables are correlated, but they're not causal. Okay, so this kind of gets us ready for our first example of an actual causal fingerprint from environmental time series data. And the example that I'm going to start with is not mine. This is done by work done by Ben Ruddle, his PhD thesis here at UIUC in 2009. But he looked at eddy covariance flux tower data. So half hourly, each of these letters is a different variable that he's measuring at a flux tower. And each arrow between different variables is indicating a transfer entropy based link. The text is kind of small, but you can see that each link is associated with some strength and some time scale of interaction. So he looks at forcing versus feedback types of interactions, kind of, draws these subsystems of, these like kind of that lima bean looking thing as like a subsystem of groupings of variables that behave in similar ways. And he looks at non-drought. So this is over a 1 month time window in I think July of 2003, that was non-drought conditions. And basically compares that to a drought condition network. And you can see, I won't make you stare at these arrows for too long, but basically what he finds is a breakdown of subsystem connections during a drought condition. So some of that kind of regional subsystem interactions do not basically occur during a drought scenario. So this is a really interesting way to kind of characterize interactions within a system, but we kind of need to keep in mind that this is all pairwise relationships. So just one thing causing another thing. And any of the subsystems and things are kind of semi-subjective because he's just kind of grouping variables that tend to behave similarly together. The next kind of level that we can look at is actually with more than one source variable. So now we're going to look at two sources providing information to a single target, and we can apply something called information decomposition. And in information composition, we're now looking at this total orange and green overlapping area. So this is the total information that two sources provide about a target. So we're really reducing the uncertainty of our target even more by including more and more information sources. And it turns out that this information can be decomposed into redundant and unique and synergistic information types. And this is going to be a major sidetrack, but I want to stop thinking about these sources as environmental time series data for a minute and start thinking of them as like singers and a duet. So each source is going to be like a singer or a recording artist, and you are the listener and you're listening to whatever duet that you're thinking of right now. And what I think about is there's lots of different types of duets. And the first type of duet that I thought about is kind of like when two singers, like a country song, they're singing the same lyrics at the same time. So they're kind of harmonizing, but they're singing the same song at the same time. These singers are providing redundant information in terms of the content of the music. So they are overlapping in the information they're providing you as the listener. There's another type of duet where these are like a lot of pop songs are like this, where you have like a rapper and then you have a hook. So you have, the catchy hook song and then you have the rapper goes and they kind of like take turns. I would say that these two artists are probably not even in the same recording studio. They are providing you unique listening information, right? So you are kind of getting a unique source of information and you're kind of switching back and forth between singers. Finally, the last type of duet that I thought of is what I think of as like the Lin-Manuel Miranda Broadway musical type of duet, where you have two singers and they're singing their own individual stories to you at the same time. So they're kind of overlapping in their song, kind of in a round or something almost. And they are providing you with synergistic information, kind of giving you a whole is greater than the sum of the parts type of experience. So they are providing you with excess information that's kind of like saving you time, right? Because you're getting their songs at the same time. Okay, so that's the 3 ways that information can be provided to you via a duet. Similarly, back to environmental time series variables, they can provide information in those same ways all at the same time. So variables are providing information to the target in some type of combination of redundant uniqueness and synergy. All right, so that leads us into another kind of concrete example of how we applied this type of framework. And what we did here was study a multi-year drought in Southern Sierra, California, using two eddy covariance flux tower sites. And we looked at how drivers of ET changed from the 2010 to 2015 time range. So with this bar chart here at the top, we can see that both of these sites really experienced very similar rainfall conditions. But it turns out that the higher elevation sites, so the red PC site here, the vegetation at that site had access to deep groundwater sources. Meanwhile, the lower elevation site did not, and the lower elevation site experienced a lot of vegetation mortality. And you can see this kind of reflected in the latent heat flux, sensible heat flux, and carbon flux averaged from each year. Basically, the blue line has a more drastic response through the course of the drought, and the red line holds more steady, and that's basically explained by this higher elevation site having the access to the deep groundwater moisture. So the vegetation roots are deep enough to get that soil moisture. Okay, so we looked at this in the context of what are the information sources, particularly to evapotranspiration. And so what this is going to show here is these two circles are for each of the two sites. So the PC is the higher elevation site. And the kind of the black bars are going to be the information that latent heat flux or evapotranspiration receives at each site for each year. And first, I'm just going to show you unique sources of information. These are all different meteorological and soil variables measured at these sites. They're really similar behaving up until 2013. And then as the drought really progresses, 2014 and 2015, we see that they really diverge in terms of the information to sources to latent heat flux. Specifically, the lower elevation site is only responding to soil moisture. All the vegetation is dead. And so really it's just evaporation. There's no transpiration, so just soil is driving. And meanwhile, the higher elevation site, the roots are accessing deep groundwater that we're not measuring at the soil surface. So it's disconnected from the soil variables, and it's really just being driven by atmospheric variables that are driving transpiration, which is still occurring because the vegetation is still active. So that's part of the kind of information story. The other part is there's obviously a lot missing from this, and the part that's missing is synergistic sources of information. So all these colorful bars that kind of make this look like a messy cobweb, these are all information sources that are actually from pairs of variables. So a lot of the information content in the system is really kind of embedded in not just knowing one thing, but in knowing two things. So that is an example of information decomposition. Okay, so I'm going to go one more kind of level up here. So that was, first I started with pairwise. This was kind of like triplets of variables, so two sources, one target. We can go pretty far beyond this by considering what's called causal histories. And this is looking at the entire evolutionary dynamics of a system. And typically these are shown with something called directed acyclic graphs, or DAGs. And in these methods, basically we're looking at multivariate and multi-lag interactions. So in a DAG, basically these are the time series variables, and we're just showing them with current time lagged, lag 1, lag 2, lag 3. So we're just kind of showing that a given target variable, say, so it's like W at time t, that target variable can be a target of information from multiple other variables at multiple other time lags. So this example is from Peishi Zhang, who was a more recent PhD student than me at UIUC. And this DAG looks a little bit like a messy hairbrush, but he's actually looking at interactions between stream chemistry variables, flow rate, and pH in a stream. So here we can see that, and this is, I think, 7-hour resolution time series data. And we can see this black dot is pH at time t, and he's looking at sources of information to pH at different time lags from all of these cations and anions in addition to flow rate. So all the linkages indicate network connections from lag to lag. And he's specifically looking at these two sources that have the red squares around them, or aluminum and sulfate, and how those two sources provide information to pH. conditioned on all of those yellow variables. So here, we're kind of breaking it down still into a two source, one target sort of problem, but in those two sources, we're kind of embedding the knowledge of the histories of all of these other time lags and variables. So then what he's doing is he's also breaking it down into information decomposition. And he also finds a large amount of synergy in this type of relationship so that these stream solutes are providing information together that they're not providing separately or individually. And I won't talk about these examples specifically, but we can kind of like, all of my previous examples are kind of site-based where we have like data from a single site, an eddy covariance flux tower or a stream chemistry gauging station. We can also think about interactions and causality kind of spatially. So these are just two examples. One is from Jakob Runge in 2015, and one's one of my papers from 2019. But basically both of these are using gridded spatial temporal data. And this is looking at connectivity between surface pressures in different regions of the globe. And then the US one is looking at the predictability of rainfall occurrence in different catchments and how different aspects of information flows between rainfall occurrence are sort of increasing or decreasing across the US. So we can also think about these interactions at different levels spatially. Okay, so just a recap of that, there's different levels that we can address causality from our time series data. We can look at pairwise couplings, joint interactions, really highly joint interactions and causal histories. And just to mention, like all of this is really just a microcosm of all the possible approaches to a causal analysis of data. So this is a recent review paper that has about 550 different references in it, all of which you are welcome to explore on your own. But all that I've talked about is probably like 3 or 4 of those references. So there are many different, branches of thought and examples of causal approaches to observational data. Okay, so that was how to, leverage our data and look at causal interactions. The next thing that I wanted to talk about today was the functional performance of models. So in order to talk about functional performance, first we have to compare that with predictive performance. And predictive performance is probably what you're normally thinking about when you're thinking about like, how is my model doing? Is my model any good? So predictive performance, you're focusing on the target output of your model and the observational, like your validation data. And you might make a scatter plot, you might look at the residuals, you might look at the root mean squared error, the Nash subcliffe efficiency, the flow duration curve, lots of different ways that you might evaluate your model. But you're really just looking at this comparison between observed and modeled data. Meanwhile, functional performance is looking at specifically how the sources of information provide information to your observed versus your modeled output. So similarly to the previous part of the talk, we can consider these interactions as being pairwise. So how does, one source provide information according to my model versus according to my data? Or we can think about them jointly, or we can think about them in a multivariate way with causal histories. And finally, we can also think about interactions between the sources themselves, and this actually has implications for how those sources can provide information to our target. So basically, functional performance is any type of measure that tells us how our models are replicating process interactions. Okay, so my first example of this, this is from Andrew Bennett's PhD thesis and published in WRR. He looked at 3 different streamflow models. And basically you can see from this annual average plot that one of these things is not like the other, right? So the green line, which happens to be the SUMA model, has a definite, different behavior in runoff than the other 2 models. And there's no truth here, so I'm not actually looking at like what the actual flow rate is, but this is a snowmelt dominated catchment. But you can see that SUMA behaves very differently from the other models. If we look at the transfer entropy between all of the different water balance components within these models. Each of these networks is for a different site, a different model. So each circle represents one of the three models. And each link, so each colored link indicates a couple or a transfer entropy based coupling between two variables. And I won't talk about what all these variables are, except to say that R in each of these stands for runoff. So the green bar is the information provided to runoff, which is kind of what we're looking at here. And we can see in the SUMA model specifically that the only source of information to runoff is from snowmelt. And for the other two models, there are three sources of information to runoff, including snowmelt, but also precipitation and soil moisture. And so that kind of explains the difference between the SUMA and the other two models. In terms of SUMA having this really like severe snowmelt peak, it's only responding to snowmelt, whereas the other two models have more of a balance where runoff is responding to these other processes. So this kind of gets to the aspect of how models are representing processes. So before we talk about the processes and the interactions, I just want to kind of bring up, if you haven't noticed already, and you probably haven't noticed, unless you're very familiar with information theory already, information theory actually provides us sort of a metric of predictability. And what I mean by that is if the total information, so if you can imagine this blue circle sort of like eclipsing this target, so if the total information approaches the value of the target entropy, that means that all of the uncertainty can technically be reduced and the target is fully predictable. And before we go like, yay, it's fully predictable, we have a perfect model, we're all done. Information theory doesn't tell us how to make that prediction, right? It's just telling us that it's predictable. So really, it's just an optimistic upper bound on predictability. And a nice way to think about this is from this really nice bar chart from a paper in 2013. And basically the top bar in this bar chart, so this tallest bar here, this is equivalent to the size of our yellow circle. So this is the total entropy of the target variable. Meanwhile, the second bar is the information that the sources contain about the target. So that's equivalent to this overlap in this Venn diagram. And the space between these bars is what I think of as missing information, also known as aleatory or random uncertainty. This is information that the sources don't even provide to the target. So, we can't expect a model to possibly contain this information because, our source data doesn't even contain this information to predict the target. So there's lots of reasons that, information is missing. It's, the target is just not that predictable, or we have missing observations. We're not measuring the right thing at the right time scale at the right place. Lots of reasons for why this missing information exists. However, there's another level, and this is the model level. So now this shortest bar, this is the information that is resolved by a given model. So this is the information that our model provides, that our modeled output shares with our observed output. And it's bounded by this second bar. So a model is only as good as the information that we provide it. But to the extent that there's a gap, that's what's called epistemic uncertainty. We can also think about this as information that the model is missing. So this is information that is technically available to the model. So we're giving the model the data, but for some reason, it's not properly using that data, or it's not seeing what it needs to make like a fully optimal prediction. So that kind of leads us to a follow-up question, is do models use the information that's available to them? And that's basically a question of, does this gap exist in our actual models? And as you can imagine, the answer is no. Models don't use all their available information. If the answer was yes, then we'd kind of be done here and just be like, okay, yes, our models are all perfect. But all of these three examples are all formulations of this bar chart in a quantitative way using actual models, ranging from catchment models to land atmosphere models based on gridded and LDOS2 forcing data to the Plummer experiment, which is comparing a bunch of land atmosphere models. And basically what all these studies are saying is that not only is there missing information, so the space between the first bar is significant, but to an even greater extent, our models are often using half or less than half of the information that's available to them. So all these papers are, entire studies within themselves. But the main conclusion is that models have room for improvement in both their parameterizations and their structure, because we have information that, somehow we are not actually able to leverage to make the best possible prediction. So a follow-up question here, though, is, okay, like they don't use all of their available information. Exactly how do they fail to use this information? And that kind of brings us back to what is the information that they're not seeing, and particularly what processes are they not properly representing? So this is just one example of looking at the functional performance of models. This is work from my PhD student, Mojgan, who graduated recently from the University of Colorado, Denver. And what she did was look at eddy covariance carbon fluxes from several different flux towers in agricultural ecosystems. And she looked at 9 different source variables as kind of like potential sources of information to carbon flux. And so these are the 9 sources. So in these heat maps, basically every square in the heat map is a certain pair of source variables. And we basically have, this is just based on her observational data, the synergistic, redundant, and unique types of information. So this is kind of the balance between, what type of information is a certain variable providing. So you can see that these observations are dominated by unique followed by synergistic types of information, and there's a couple pairs of variables that provide redundant information about carbon flux. So what Mojgan did next is she took this and basically mapped these observed information flows to several different types of models. So she looked at machine learning models. So she looked at linear regression. This is kind of a simple base case, a random forest model, and a deep learning model called long short-term memory, so LSTM. And basically in these kind of nine plots here, a red color means that the model underestimated a certain type of information, and a green color indicates that the model overestimated that type of information. So you can kind of see, don't stare at any particular source, but in general, models tend to underestimate synergistic types of relationships and overestimate the unique components of the relationships, which is kind of saying that these models are sort of learning the unique information that's available from a single source, but they're not learning information that's available jointly or sort of in a more complex way. So they're not correctly capturing those synergistic types of relationships. And this varies between sites and between training data experiences. Particularly the LSTM model is more data hungry, so the LSTM actually gets better and better. So here it kind of looks like the random forest is doing really well, but they kind of vary depending on how much data is available. But they all kind of show that general property. Okay, so this is all just functional performance and do models capture these types of information? But a follow-up question here is, how do functional and predictive performance relate? Because, we still care about whether our model is getting the right answer, right? So we still care about whether these models, which one is the best in terms of its predictive accuracy. Okay, so to talk about this, these authors in a paper in 2019, including Ben Ruddle again, they looked at the idea of potential trade-offs between functional and predictive performance. So this space here is basically plotting functional versus predictive performance, and I overlaid this star to kind of show the ideal case. So here a lower value is better. And you can kind of think of a point in this space as a single model. So a single model has some whatever measure you're using of predictive performance, and it has some functional performance of some certain relationship or a combination of relationships. And here we're kind of thinking about like changing a parameter and running the model again, and you're getting a different predictive performance and a different functional performance. So here model A is kind of an example where as you improve one type of performance, you're also improving the other. So this is kind of like the ideal model case where yeah, like you change a parameter, you improve the prediction, but you also improve the extent to which interactions are getting replicated. However, there could be other hypothetical cases where you might calibrate your model to have a better prediction at the expense of some process, and that would kind of indicate a structural error in the actual formulation of your model, right? So you can change a parameter to maximize your performance, but you might be sacrificing another type of performance. So they actually looked at this for a single model. So this is a multi-layer canopy model. And they looked at latent heat flux, and they looked at just varying a single parameter in this model. So big model, one little parameter. This is a parameter that's related to stomatal conductance. And what this is showing here, each of the colors are a different source variable, and it's just showing functional versus predictive performance with that source variable. So how does that source variable provide information to latent heat flux? And what this kind of shows is that it is you do see that kind of like bowl shape in most of these. So this is kind of saying that for the most part, with a few exceptions, as you're improving predictive performance, so as you're going downward on this plot, you're also converging on a better functional performance. But that was just latent heat flux, and I didn't pop up for some reason here. They don't see the same thing for other variables. So for example, with sensible heat flux, they actually see some squiggliness in this relationship where you can change a parameter for better predictive performance, but sacrifice another type of performance. So this paper was really interesting in terms of just starting to think about how models are sort of reproducing this, these interactions and what that means in terms of like what predictions they're making. But it kind of led us to a weird follow-up question is, what is the potential for a model to provide a certain type of information? So what I tried to look at here was, say you have a given model structure, maybe it's really simple or maybe it's really complex, maybe it has parameters, maybe not. But maybe there's a way to say that like a certain type of model can't even possibly reproduce a certain type of process that you observe in your data. So here, this idea, basically we went through several like toy all the way up to real ecohydrological models, and looked at how sources and the model structure, so the source time series data combined with the actual equations or framework of the model, sort of combine with each other to lead to certain types of functional and predictive behavior. So what we tried to look at was what types of interactions can a model possibly represent? For example, if you have a really like simple model and suddenly you see like a really complicated response in your data, you kind of just know that your model's not going to be able to replicate that. And also, can this vary depending on the sources themselves? So can we have a situation where sources are interacting with each other and kind of influencing the way that the model can sort of see that information? And to do this, we look at functional performance along an axis of the dependency between sources. So I'm going to skip these, first kind of toy examples and go straight to an ecohydrological example. And basically what we looked at here is we looked at 4 different models. So this SFE is the most simple possible model of latent heat flux. And the SUMA NN2 is a hybrid machine learning and process-based approach. So this is a pretty complex model. It's a model called SUMA that is a process-based model embedded with a neural network in kind of like a feedback situation, and using that to predict different ecohydrologic fluxes. And what we do here is we pick out 2 sources. So we look at air temperature and relative humidity, and basically how those 2 sources provide information to the Bowen ratio, which is the ratio of latent and sensible heat flux, or the ratio of sensible to latent heat flux. Okay, so the stars here are just indicating like the best performance. So it's kind of a little counterintuitive because lower values here indicate better functional performance. And the x-axis is showing the mutual information between my 2 sources. So air temperature and relative humidity. And we see that all the models kind of have this same behavior where as air temperature and relative humidity become more and more related, the model gets better and better. So like the model actually has higher functional performance. It turns out it actually has higher predictive performance also, as the correlation or the dependency between air temperature and relative humidity increase. And the other thing to notice here is that this pink line is the summa NN2, so this is our most complex model, and it shows usually the best behavior, so the best performance, but especially better performance when the sources are really independent. So when we have kind of like a worst case scenario from the information perspective, the neural network hybrid approach is actually doing the best at kind of handling that source data. So basically it's easier for models to use redundant information is kind of how I think of it. For example, say our model has some structural deficiency where it's like, it's not using relative humidity the way it should. So it has some incorrect process. If air temperature and relative humidity are really highly linked with each other, it's actually kind of able to use the information from air temperature to kind of substitute for that loss. So it's models are able to use information when it's provided redundantly. Okay, so the main conclusions here is that dependencies between sources also impacts how the information gets used by a model. So it impacts how the model sees that information. Okay, so a recap on this segment is basically there's a lot of different ways to think about models from a causal perspective. We can think about how models represent processes, whether or not the models are utilizing the information that's available to them or how much information is available, how models respond to parameters, so calibration and trade-offs in functional and predictive performance, and finally, how models handle dependencies between input data variables. Okay, so that brings me to my short conclusion, just a little bit expanding a little bit on causality related research. Okay, so I mentioned this review paper earlier. So this review paper with its 550 references, basically it kind of poses that the cycle of understanding complex systems is kind of accelerated due to the emergence of this more data-driven methods, more models, and kind of enhancing or speeding up the way that, we're translating our observations into theories, into predictions, running experiments, and then again, going back to our data collection or our observations. And so a couple of things I just wanted to mention. There's a lot of ongoing work. First of all, work that identifies causal relationships directly from data, which is a lot of what I've been talking about, but also identifying governing equations themselves, looking at AI, artificial intelligence and causal reasoning there, and finally seeking to identify concepts like emergence that are kind of, often looked at sort of qualitatively. So just as one example, this is an example of learning equations themselves. So AI Feynman is basically a ML embedded algorithm that is performing symbolic regression. So instead of taking the data and looking at a causal network and looking at what's it's kind of taking that a step farther and looking at what is the equation that possibly or probably or definitely generated that data set. So just to zoom in a little here on this big thing, it's taking data directly and then saying, this is the equation that this data came from in the presence or absence of noise. So this is kind of an example of people that are trying to sort of reverse engineer governing or generating equations and actually understanding processes directly from data. Another example, everyone is probably familiar with ChatGPT. Students definitely are familiar with ChatGPT. There's a lot of work in kind of understanding how ChatGPT and large language models, so LLMs in general, are seemingly providing us with reasonable causal sorts of information and sort of understanding how they are either doing causal reasoning or they are kind of replicating our own causal reasoning that we provide in our giant sets of textual training data. So there's a lot of research on that. And then finally, causal relationships are part of the concept of emergence. So basically, the idea of emergence is that at each level of complexity, entirely new properties appear. So for example, if you just look at an individual bird and you look at its behavior, it's really interacting very simply with other birds. It's obeying simple rules. However, that wouldn't lead you to predict these kind of, everyone has seen these flocks of birds that kind of fly in beautiful formations, and a hawk comes through and they kind of make beautiful shapes. So you can't necessarily predict from knowing individual components, behavior or phenomena that emerge at a higher level. And this is highly related to causality, because it's kind of looking at causality at different levels of granularity in a system and understanding, how a behavior emerges from a collective combination of smaller behaviors. Okay, so as a conclusion, hopefully this sort of just shows you that we can go a lot farther into causality relative to just the correlation is not causality and like, well, we can't do anything. And we can really probe interactions in environmental and water systems. So this kind of has, in context of, being able to leverage the large amount of data that we have currently, and possibly target new experiments. And, it's all about data, and we all love data. So that's it. I want to thank my collaborators and co-authors. A lot of the work that I presented isn't mine. So I call them influencers, or authors of some of the referenced examples, which I have listed here. And yeah, that's it. Thanks for having me, and thanks for joining on Zoom.
Okay, let me just bring up the chat window so we can see people online. Maybe participants. We can start. Any questions in the room?
I've been thinking through assumptions that go into many of these, and I know, of course, there wasn't time to go through all the assumptions that go into each technique. But I think one of the assumptions that kept jumping out to me is the assumption that using more information makes the predictability better, or makes the prediction better, I guess is a better way of saying it. Is that always true? Are there situations where adding data, adding information makes the predictions worse?
Right, yeah, that's a good question. Yes, so it's not necessarily that more data equals a better prediction, or like, adding source variables improves your prediction, because often you have kind of a saturating condition where, you add variables and it doesn't do anything. So it's kind of all a matter of, are you looking at the right variables that are actually the causal influences to the system? So it's easy to, I guess, formulate an idea where, you input the wrong data and, you see some certain level of predictability, and that, definitely, more data doesn't necessarily equal more information, but more information equals more predictability, I guess. But yeah, that's a good.
The simple example that came to mind is if you have a key variable, from physics that it's key, but the observations are wrong for some, the instrument broke.
Right. Right.
Is that an example of?
Right, that would be an example of, I guess that'd be an example of the missing information or the aleatory uncertainties. So that would, you would look at that and you take your observational data that's bad. And you'd see, well, the observed data is not even providing information about the target, like whatever you're trying to make a model to predict. And so that would lead you to say well, the information is not there anyway, and you have a ton of data, but very little predictability. And then your model is sort of the garbage in, garbage out sort of scenario, right? Where you're taking in bad data and you couldn't have expected your model to possibly. And so this is kind of a way to almost look at what you have, because if your model's not doing well, it's either a problem with your data, or it's a problem with, it's either that, the predictability is not there, or your model's not doing well. And, sometimes it's hard to tell which one is which. Yeah.
Can you introduce bad data into your model on purpose, right? Because in the real world, when you're trying to predict new value, the information you're given sometimes is flawed. So is there value in training the model on bad data to see if you can kind of generalize around it?
That's a good question. Yeah, I feel like that's
confusing.
Yeah, I think there's been some good examples of like LSTMs being able to tell whether the observational data is bad. So it's like you train, LSTMs on this really large network of catchments, and there's some sort of precipitation bias in part of the country. And it's like they can actually kind of overcome that by learning like what the real, like where the information content is really maximized. And kind of like throwing out the bad data, yeah, that's a good question, I don't really have a good answer.
So in sparser sample situations, like in modeling the geology, which tends to be sparser sample, not a traditional time series kind of system, but we use models, conceptual models and statistical models with different predictive kind of constraints. Has there been any looking at the entropy-based models that are there to see if there's types of distributions, types of entropy patterns that might be distinguishable? Like this entropy pattern has a unique causal relationship or has a semi-ambiguous one. It can be used as a model for sparse sampling areas.
Yeah, so you just mean times when you don't have like high resolution.
Yeah, I mean, I
data,
might
but you have-
sample, I might collect the sample of a mineral distribution. And it's not enough to really estimate the structure there, but I might say, well, based on this, I'm gonna go with, based on what I know of this system, I'm gonna go with a log normal type of distribution with this kind of. You know, if I had entropy as a useful modeling parameter, could I say, well, I've got this kind of entropy here and this kind of entropy over there?
Yeah, that's an interesting thought. I guess one thing that we have looked at a little bit is, you know, just using entropy, you know, so it's like you're a little bit limited and you can't look at the full, you know, causal history or whatever, given very limited data, but you often can look at some of the lower level measures like entropy and look at the level of variability. So it's kind of just giving you a different type of measure. It's like, you know, you have the standard deviation and you have the mean and you have the entropy, and the entropy is telling you something about the distribution of that variable, which might be relevant in, you know, knowing its predictability or knowing whether it varies across space or.
Is like mutual information and are they more robust estimation than like two parameter types of statistical models?
Is mutual information more robust?
Yeah.
I guess I didn't talk about like statistical significance testing of any of these at all, but that exists. So yeah, like any measure of mutual information or transfer entropy or causal histories, it's all that there is a way to determine the statistical significance and like basically like a p-value associated with them. So I wouldn't say that there's a big difference in like the statistical confidence of the like traditional like correlation measures versus information theory measures.
Are there any online? I haven't seen any here.
I
Okay.
don't see anything in the chat.
The example you showed of the, great talk, by the way. I had lots of great stuff. The example you showed with the connections, kind of the schematic of connections in July with, without drought. And how things, relationships sort of went away, came on, maybe in some cases fundamentally changed. Something that deal with a lot with some extreme like drought. So with all this framework, how do you develop a model that can perform well overall, as well as in environments that it may only have a very sparse sample size of seeing before it's put out, if that makes sense, and in an environment where the relationships that would be pieced together that would work 99% of the time really well fail in times when the impacts actually matter, if that makes sense.
Yeah, so sort of like rare events, I guess, or like
that's a
models
really
availability
better way to put it. Yeah.
to capture events that you don't see very often, like a flow peak or a drought or something
Yeah,
like
but
nature.
importantly, events that you don't see very often, but also have different relationships than the
Right,
lesser.
Yeah, so I guess like I think that, you know, if you have a model with good functional and predictive performance and a model with good predictive performance and bad functional performance, so for some reason you have two models and they have the same root mean squared, like root mean squared error, you would say like, I don't know which of these models to use. And I guess all I could really say is that if you looked at the functional performance and you saw that the functional performance of one model was higher than the others, the model is better replicating something about an interaction, that you could hopefully trust that other model. Like you kind of have a reason to choose that other model because it has better replication of processes. And I guess you could look at that in the context of like a specific rarely seen process of like, you know, when the soil moisture is really low, are we properly replicating this type of interaction? Like, even though we've only seen it a few times, like in our historical data. So yeah, that's a good question. It's like, you know, when does functional performance say something about how your model is behaving versus like what, you know, how it's behaving under certain like extreme conditions? Yeah, that's a good question.
Any more questions in the room? Online? Do you have any questions? One more time in the room? One more time online? Well, Allison, thank you. Let's give her one more round of applause.
Can I leave the meeting?
Yeah.
Okay.
And
Thanks,
thank
everyone.
everyone for participating. And hopefully we'll see you again soon. Bye-bye.